Okay, hi everybody again. Well, we live in unusual times, and so I'm doing this unusual thing of trying to answer whatever questions you may come up with about science. I've been studying and working on science for most of my life, and learned a few things. So we'll see how I do on answering your questions. I did one of these last week, and this is kind of back by popular request. Okay. Gosh, we've got questions already. We've got physics coming already. All right, I'm going to do so. Got a couple of questions here. So let me start off. Thomas asking, what are protons, neutrons, and electrons made of? Okay. Well, the story is a bit different for. So first of all, let's remember where we run into protons, neutrons, and electrons. So atoms have a nucleus which contains protons and neutrons, and they have electrons which are kind of sort of orbiting outside the nucleus. They're kind of hanging around outside the nucleus. So it's a different story. Electrons are a different kind of thing than protons and neutrons. In the language of physics, electrons are examples of things called leptons, and protons and neutrons are examples of things called baryons or hadrons. Those are fancy words which probably get used if you study physics in college or graduate school and maybe don't get used by anybody else. But they're sort of two different families of kinds of things. Okay, so let's start off with protons and neutrons. So it was discovered in the 1960s, early 1960s, that protons and neutrons weren't just sort of point things. They were things that have a definite structure inside. And actually they have, the diameter of a proton is about 10 to the minus 15 meters, which is otherwise known as, let's see if I can do the conversion, 1,000 trillionth of a meter. So very small, but not zero. So what's inside protons and neutrons? Inside protons and neutrons, there are things called quarks. That was kind of, quarks were originally, a person I knew well actually, kind of came up with that idea back in the early 1960s that there might be something inside protons and neutrons. So roughly, inside protons and neutrons, each one of those has 3 quarks inside it. And like a proton has 2 up quarks and a down quark, and a neutron has 1 up quark and 2 down quarks. And that's kind of what makes those types of particles different, is they have different quarks inside them. Now, one of the tricky things is you might say, well, why don't I have, why aren't there bottles of quarks around? Why, protons and neutrons are very common. Why do we not have quarks that we can actually see? Well, it's a very tricky thing. So quarks are these little particles which seem to be more or less point particles. They more or less have 0 size. Not quite. We'll talk about that in a minute. But the question is, why do they never get out of protons and neutrons? And the answer is, there are these things called gluons, which are another kind of particle. And between these quarks are kind of bound together by gluons. They're gluons that are being exchanged between quarks, and the gluons are pulling very hard on these quarks. And so far as we can tell, it's not possible to get a quark outside of a proton or neutron. You can't ever pull it outside. So what happens roughly is this. So if you look at, for instance, if you look at, let's say, the force of gravity, you might know as gravitational masses get further apart, the force of gravity between them goes down. It's actually an inverse square law. So if the distance between the objects is r, the force between them is proportional to 1 over r squared. Okay, it's the same thing actually, the same exact force law for charged particles that have electric charge. They also have a force law that goes like 1 over r squared. So as you make them further and further apart, the force between them gets less and less. Okay, so gluons make a force between quarks, and the really weird thing is that the force between quarks actually, instead of going down as you pull the quarks apart, it actually goes up. It goes up roughly as the distance between them goes up. The force increases as you make the distance go up. It's roughly proportional to the distance between the quarks, the forces. So that means that you try and pull these quarks apart, it gets harder and harder and harder to pull them apart. So if you try and actually get a quark all the way out of a proton, you can never do it. So So what's inside protons and neutrons is this kind of soup of quarks, mainly 3 quarks, and a bunch of gluons that are holding these quarks together. It's a little bit confusing. There's a whole kind of cloud of quarks and antiquarks. We can talk about antiquarks and antimatter different time, but roughly it's this sort of cloud of particles inside protons and neutrons. So that's the story about what's inside protons and neutrons. So you might also ask, well, what's inside quarks? What's inside gluons? Well, the answer is nobody knows. You can ask the same question about electrons. As far as anybody can tell, electrons are perfect point particles. It's like they have no, if you say, what's the radius of an electron? What people have always said in physics is the radius of an electron is 0. It is like a perfect geometrical point. Now, I personally think that isn't correct. And actually, I happen to have been very recently working on kind of understanding what might be sort of underneath fundamental physics. And I actually think that in the end, it's going to turn out electrons are actually not point particles. They actually have a size. It's actually very, very, very small. What's inside electrons, I think, is related to kind of how space works. See, space, normally we think of sort of the universe. We say we can position things any way we want. We can say we put this electron at this particular position. If we specify it by a number, it might be, position, 1.237582464, et cetera, et cetera, et cetera. We could just go on as many digits as we want. We can precisely say we're going to put this electron at this precise place in space. I mean, how we actually do that with an experiment, we might not be sure, but at least when we're doing theory of physics, we can say we put this electron at this precise place. Okay, well, that would work fine so long as space is itself continuous. If space was instead some grid where you could say, oh, we can only put an electron at this position on the grid, or this other position on the grid, or this other position, you wouldn't be able to do this thing of saying you can put it anywhere you want. Well, I actually think that in the end, it's going to turn out space, it isn't quite a grid, it's more like a network. And in fact, electrons correspond to these kind of features of the network. It's kind of almost like little knots where you have little threads of network that connect pieces of space, and electrons are kind of like little knots in that network. And in fact, that means that, in a sense, when you say what's inside an electron, what's inside an electron is a kind of space, but a funny kind of space. But it's all that's physics that doesn't yet exist, because it's physics I've been working on that if it wasn't for this pandemic, I would be telling people much more about. But anyway, so that's kind of the story of electrons. Is the usual theory in physics is there's nothing inside electrons; they're just point particles. I think that isn't correct. They actually have a small extent, and sort of what's inside them is a special version of ordinary space. Same with quarks. In physics, as it's been thought about for the last 50 years or so, the idea is quarks are also point particles with nothing inside them. But again, I don't think that's correct. Okay, long answer to that question. Let me go back here, and I might also say, when you start asking about very small things like electrons, there are lots of tricky phenomena that happen. And maybe we'll talk about them some more later, about this thing called quantum mechanics, that kind of is all about the fact that you can't, when you think you know where the electron is, maybe it isn't quite there, you can't quite localize it, and so on. Long story. All right, let's come to some other questions here. Okay, there was a question at the beginning. If neutron stars are just made of neutrons, how come they produce light? I don't think they usually produce light. They produce radio waves. If they produce, so let me explain a little bit. I think I talked last time a little bit about neutron stars. So when a star, billions of years from now, our sun, for example, will kind of run out of fuel, and it will just become a smaller star. But some other stars a bit more massive than the sun can end up having these giant supernova explosions, And what gets left over after that explosion is often a neutron star, which is kind of something about the mass of the sun, but compressed into something maybe 5 miles across. So it's a very, very dense object. It's actually very much like the nucleus of an atom, except very big, like a 5 mile across atomic nucleus, all made of neutrons. So the question is, how do you even know that there's a neutron star there? Because like a neutron, it's just this big lump of stuff that is like an atomic nucleus. How would you know it's there? Okay, well, it turns out that, so one of the things that happens, boy, this is some complicated physics. Let me try and explain it. So you probably know that the Earth has a magnetic field. So that means that's why compasses work. So the Earth has a north and south magnetic pole. It's like a giant bar magnet. The Earth acts like a giant bar magnet, and that's why a compass needle can point towards the north and south poles. And so the Earth is kind of has this magnetic field. What produces the magnetic field? It's probably produced by essentially electric currents in the liquid core of the Earth. It's not completely clear how that works. And one of the things that's weird is you think that the North Magnetic Pole is to the north, and it is right now. The North Magnetic Pole is somewhere in northern Canada right now. But over the course of history, the magnetic poles of the Earth actually move around. And it's not been many hundreds of years since they've been actually in quite different positions than they are now. So that's probably because of changes in the flow of the kind of molten rock in the center of the Earth that's changing and causing the magnetic field to be in a different orientation. But anyway, so the Earth has a magnetic field. The Moon, for example, does not have a magnetic field. Jupiter has a big magnetic field. The Sun also has a magnetic field. And it's thought that most stars have magnetic fields. And so that means that there are essentially electric currents in the sun that are producing this magnetic field, and it's like a giant bar magnet. Okay, so what happens is when this star has a supernova and it kind of compresses down to this neutron star, the magnetic field can't go away. The magnetic field has to be that it had when it was a big sort of a large star. Is still there, but it has to be sort of compressed down to kind of fit around this little tiny neutron star. And so that ends up with a pretty intense magnetic field. And so what happens is this thing is like a bar magnet, a really quite strong bar magnet. And boy, this is some complicated physics. Okay, so what happens is that electrons spiral around the magnetic field lines of this bar magnet. And the same thing happens for the Earth, actually. There are electrons that come from the sun, for example, that spiral around in the magnetic field of the Earth near the north and south poles. And so, for example, that's what causes the aurora. The aurora, if you go to the northern, far up north, and it's good weather, and you let your eyes get dark adapted and so on, you'll see this really cool, it's usually red, green, all kinds of other colors, sort of curtain-like pattern in the sky. That's the aurora, and that's produced by electrons that originally came from the sun, spiraling around the magnetic field near the north pole of the Earth, and causing particularly things like oxygen in the upper atmosphere of the Earth to produce light of different colors, in kind of the same way that a fluorescent light bulb produces light. It's sort of the same rough idea of how light is produced in the upper atmosphere in an aurora. But anyway, so that's a place where you're producing, in that case, it's producing light because these electrons are hitting oxygen, other things in the upper atmosphere. Okay, with a neutron star, electrons can be kind of made. They spiral around in the magnetic field, and they spiral around really quite fast. And one feature of electrons that are spiraling around like that is they produce, they emit radio waves. And that's true in general. If you have, when you have a radio antenna, the way the radio antenna works is that it's making electrons go up and down, up and down, up and down at a certain frequency. Like a typical cell phone, it might be 2 billion times a second, 5 billion times a second, that kind of thing. The electrons are going up and down in the antenna that's on the side of your cell phone. So it's the same type of thing when electrons in magnetic field of a neutron star going around really fast, and they're kind of being made to go around in these circles, and that produces the same effect of making radio waves that happens in something like a cell phone. But those radio waves are pretty intense, and we can detect those radio waves, even though these neutron stars may be 1,000 light years away, or really far away across the galaxy. And so the result of that is, okay, so I have to explain one more thing. Gosh, I don't get to explain this kind of stuff very often, so I'm not quite sure how much there is to explain, but let me keep going. So another feature of neutron stars is they typically spin around very rapidly. And that's kind of for the same reason that the sun is spinning at a certain speed. If it were to be compressed down to a neutron star, it would spin much faster in order to conserve its so-called angular momentum. So, okay. So anyway, this neutron star, it's spinning around very rapidly. It has electrons that are producing radio waves. And what happens is, as the thing spins around, it's essentially producing because the way the electrons, gosh, a little complicated. In the magnetosphere of a pulsar, which is the kind of sheath of magnetic stuff around the pulsar, it's not quite uniform, and so there'll typically be one direction where it is producing more radio energy, radio waves, than in other directions. And so the pulsar turns around, and as the pulsar spins around, I cheated here. I already told you the answer. So this neutron star is, I should have said, just neutron star is spinning around. As it spins around, it'll send this beam of radio waves in a particular, the beam of radio waves that it's producing will spin around as well. And so if we're over here on the Earth, as this neutron star spins around, every so often its radio beam will point towards the Earth. And so if we are listening on the right radio frequency, we'll be able to essentially hear that radio signal coming from the neutron star. Okay, so back in 1968, people were doing radio astronomy. They were trying to use telescopes that kind of detect radio waves, and they discovered this strange phenomenon that they were hearing pulses, in radio pulses that were coming from particular stars in the sky, particularly the Crab Nebula is one famous one. And so it's like, what was this? I think I mentioned this last time, but you hear this kind of pulse, and it's sort of regular pulse. And the first guess was, gosh, that must be a beacon of some extraterrestrial civilization that's saying, hello, we're here. You know, it's like a navigation beacon or something from an extraterrestrial civilization. And that's what, for the first 2 weeks, I think people thought that's what that might be. And then they realized, no, actually, it's a neutron star. And those things are called pulsars, pulsing stars. And pulsars produce these sort of pulses of radio energy. I don't think that they produce, I don't think there's visible light that gets generated. If there is visible light, it comes from a different phenomenon of accretion disks, where there's matter that's kind of being dragged into the neutron star. But I don't think that happens with neutron stars. It happens with black holes. I don't think it happens with neutron stars, but I might be wrong about that. But in any case, the pulsars, we now know a whole bunch of pulsars around the galaxy, and they're really cool objects, because they're these whole stars that spin around, like they're even millisecond pulsars, which means they spin around 1,000 times a second. The whole star is spinning 1,000 times a second and producing a radio signal that is about 1,000 times a second. We hear a pulse from it. And you can do all kinds of weird things. Like, for example, let's say you wanted to work out how to do GPS in space. So GPS is how we find how cars and planes and other things find their position on the Earth. And the way it works is there are satellites orbiting the Earth, a constellation of, I don't know how many it is these days, maybe 60, 70 satellites orbiting the Earth, that each produce pulses with a known interval. And so when your GPS receiver can tell, oh yes, the pulse I got from satellite number 17 took exactly 21 milliseconds, 21.125864 something milliseconds to arrive, because the pulses they have a certain code that tells you when the GPS satellite produced that particular pulse, and you know when you measured that pulse. So that allows you to work out, because you know the speed of light, you can just work out how far away the satellite was, and that tells you if you know 3 satellites, you can triangulate to find your position. Okay, so one of the questions is, if we were in space, if we were doing some, we were going off and we were sending a spacecraft to Pluto or something, as far away from the GPS satellites that are orbiting the Earth, they're not going to do us any good in telling us where our spacecraft is. How can what's the kind of interplanetary or even interstellar version of GPS that we could use? And so one thing people have thought about is to use pulsars as kind of an interstellar GPS system, because we know where all these pulsars are. Each pulsar has a definite series of pulses that it produces, and so you can use that to figure out how far away are you from all these different pulsars, and that gives you a way to get a kind of location in interstellar space. That gives you sort of a way to do that. I mean, a more simple-minded way to do it, which is what a lot of deep space probes do, is they just have a little telescope and they look for different stars, and they say, in what is the orientation of what direction do I have to be pointed in to see this star and that star, and they do things that way. All right, long answer to that question. All right, we've got lots and lots of other questions here. Let's see. How can one improve mathematical and scientific and analytical thinking? Books to read and so on. I'm not a huge expert in what exists right now. I think, the main thing I always like to do is, when I see stuff happen in the world or I hear about stuff, I just try and learn how it works. And the web has lots of good sources of information about sort of how things work, and try and read those. Ones you don't understand, try and figure out what were the sort of underlying concepts, and try and get to understand those. I think that's a good place to go. When you really want to know sort of how things work, learning how to tell a computer what you want is a really good way to do that. I mean, I've spent a lot of my life building this kind of computational language to have us humans be able to explain to computers what we want. And I always find that the time when I really think I understand something is when I can write a little program that does the thing that I'm talking about. That's kind of my test for whether I actually understand what I'm talking about. And I find that it's a really good way to kind of organize one's thoughts, to kind of explain it to a computer. It's also good explaining it to other people, like I'm trying to do right now. Okay, I'm gonna skip to some more of the sciencey questions here. I can talk maybe a different time about more kind of computational thinking kinds of things. Okay, so the question from MC is, how do magnets work? Okay, well, there are all right. Magnets, like lumps of metal that make magnets, I can explain how those work. You can also make magnets by using electricity. And in the end, magnets, like lumps of metal, work in kind of the same way as magnets that are made with electricity, but it's a little bit tricky to explain exactly their correspondence. So let me start off by talking about magnets that are made of pieces of metal. So the most common kinds of magnets, bar magnets made of iron. The 3 chemical elements, iron, cobalt, nickel, which are next to each other in the periodic table, which means that they have adjacent numbers of protons, because the periodic table just is this table of all the different possible kinds of atoms, where each one is arranged from hydrogen, helium, lithium, beryllium, etc. Hydrogen has 1 proton, helium has 2 protons, etc. That's how the periodic table works. In one part of the table is iron, cobalt, nickel, and that's the most common thing that magnets are made of. There are also things called rare earth magnets, which are actually much stronger magnets. The most common, let's see, I think gadolinium, europium, samarium, I think, are common examples of rare earth magnets. Those are also elements in the periodic table. They're also metals, and they allow you to make stronger magnets. Okay, so how do these magnets work? Well, basically, a big magnet, like a big lump of iron that's a magnet, the way it works is it has a lot of really tiny magnets that are all lined up inside it. Those tiny magnets are actually iron atoms, and the iron atoms are themselves little tiny magnets. And the big thing that makes the big lump of metal act like a magnet is that all those little tiny magnets are all lined up. So here's the thing not to do with a magnet that you want. Don't put it in an oven. And because if you put it in an oven and heat it up, there's a temperature, it's called the Curie temperature, at which it loses its magnetic field. It loses its magnetism. So what happens is, just like if you take a block of ice that's solid, all the atoms are all lined up in the block of ice, and you heat it up, eventually it'll turn into a liquid, and the atoms won't all be lined up. They'll all be running around all over the place. The same thing happens in a magnet. So an ordinary magnet, when it is magnetized, and it is at ordinary room temperature, the atoms inside that magnet all have what are called their spins. The little tiny magnets are all lined up. And so that means you'll have trillions and trillions of little tiny magnets all lined up, and they all line up in the same direction. And so they make the whole thing act as a big magnet. If you heat it up, essentially the magnets it's like they melt, and it's long before the lump of iron actually melts, long before the actual atoms in the iron get separated to the point where the iron becomes a liquid. Long before that, the alignment of the little tiny magnets that these iron atoms are, that gets broken down, and so your magnet will lose its magnetic field. So if you care about your magnet, don't heat it up to that point, because it will lose its magnetism. Now, the good news is you can always give it back its magnetism. If you put it in a magnetic field again, it will the iron atoms will line up again, and you'll make a magnet again. Although you might make a magnet that's in a different direction than the magnet that you had before. So the way that sort of things like bar magnets, big magnets, and things work is they have these little tiny atomic scale magnets, and they all get lined up, and that's how you get one of these big magnets. And it's only certain metals that certain materials that have this feature that their atoms can line up in this way. It's still the case that if you picked out an individual atom of almost any element, it could act like a tiny magnet itself. But it's only in certain materials that all those little tiny magnets can get lined up to make what's called ferromagnetism. That's the name for the phenomenon where all the little tiny magnets line up to make a big magnet. So anyway, that's the way that that's the way things like bar magnets work. The way that you can make a magnetic field without having any of these atomic magnets. You do that by having so electricity and magnetism are closely related. And it turns out that if you have, for example, a loop of wire, and you have electricity flowing through that loop of wire, it will produce a magnetic field. So maybe I could explain another time how that really works. But basically, when electrons that make electricity are moving around in a circle, they produce a magnetic field that goes sort of perpendicular to the circle, and that's how electromagnets work, and they're very convenient. Like, for example, if you have a door that's supposed to be locked or not locked, you can do that by having what's called a solenoid, which is one of these it's an electromagnet, and that means that if there's an electric current If there's electricity flowing through this coil, then it will produce a magnet. And if there isn't electricity flowing through there, it won't make a magnet. So if you have two of these things next to each other, for example, you can say, okay, there's electric field going through these, so they make a magnet, so they're held together. Oh, you switch the electric field off, oh, then they'll break apart. So that's a very convenient thing, because it means you can have magnets that you can kind of switch on and off just by switching electricity on and off. Now, the tricky thing that's a little bit more complicated is, in some sense, the magnets that are these atomic magnets are actually made from something analogous to a loop of wire, because what's actually happening is that the electrons inside the atoms are kind of going around the atoms, just like the electrons go around that loop of wire, but it's like a little tiny loop of wire the size of an atom. And that's kind of how the magnetic field gets made in just at the level of the individual atoms in iron, for example. Now, okay, in sort of, to be really exact, there is another thing that happens. These individual particles, like an individual electron, actually is like a tiny bar magnet. And so I was telling you earlier, electrons are either of zero size or at least very, very small. And so there's kind of a question of how an electron manages to have what it takes to make a magnetic field just by just as a thing itself. And nobody knows how that works. I think this new theory that I have for how fundamental physics works probably explains that, although I don't yet know how that works. I mean, if you're interested in, there's a phenomenon called spin, which is a feature of particles. Again, I'd be happy to talk about it. It's an interesting and complicated story. Electrons have spin 1/2, photons have spin 1. All these different particles have a certain spin, and many of those particles, when they have an electric charge and they have a spin, they will act like little magnets. So, okay, long answer to that question. All right, let's see. Why is there an ultimate speed limit of the speed of light? Well, it's a good question. Well, the ultimate answer is we don't know. It's a feature of our universe. It's a very important feature of our universe, and we don't know why it works that way. Now, having said that, for example, my new theory of how physics works, we can understand, well, we can understand a little bit more about why there's a maximum speed. So the speed of light, maximum speed that anything can go at in our universe. How big is the speed of light? The thing that's worth, if you're going to remember one of these factoids about light goes 1 foot in 1 billionth of a second. So in 1 nanosecond, light goes 1 foot. So that means in 1 second, light goes 1 billion feet. It takes, so for example, to give some sense of scale, it takes light 8 minutes to go from the sun to the earth. It takes light, what is it, about a couple of seconds? No, gosh, I have to work it out. Maybe half a second or a second to go to the moon. So light goes fast, but not at infinite speed. To go across our whole universe takes a time that's about the age of the universe, about 14 billion years. Actually, it takes even longer than that to go all the way across our universe. That's sort of a first approximation to how long it takes to go across the universe. But then, the speed of light governs the maximum rate at which we can send signals. So for example, when I don't know, like when we're using the internet, for example, it's often called the ping time on the internet. So one computer will ping another computer. In low-level operating systems, there's usually a command called ping, and you say ping, and then you say the name of a computer, and it will say, oh, it took 200 milliseconds, 200,000th of a second to send a signal to that other computer and get it back again. Okay, so the ping time is this time for signal to go from your computer to another computer and get back and tell you how long it took. So the question is that in fact, is that time, that's sort of that tells you how long it takes for information to go from your computer to another computer. And in a first approximation, that is at least well, it's certainly limited by the speed of light. You'll never be able to get your computer to ping another computer faster than it would take light to go from your computer to another computer. Now, how is the actual signal sent? Well, often a lot of signals now are in fiber optic cables. So fiber optics is like, normally, you shine a flashlight or something, and you're just shining it through the air, but you can also get light to go through glass, and you can make these fiber optics where the light goes into this fiber and it bounces off the edges of the fiber, and it keeps bouncing off the edges of the fiber, and the light will just keep going through this fiber. And so you can actually have a single fiber that can be like probably these days 100 miles long, and you can just shine light in one end of that fiber, and the glass is in the fiber is sufficiently pure that the light will just keep going, it'll bounce off the walls, but you won't lose any light, and you'll still be able to get, and you'll get the light out at the other end. And so a lot of the internet is built with fiber optic cables where the speed of light, where it's light that's transmitting the signals, that's telling, that's going from my computer camera to onto the internet, and so on and so on and so on. Now, actually, a little bit of a footnote to that: light, the speed of light that you hear about, 1 foot in a nanosecond and so on, that's the speed of light in a vacuum. It's very close to the speed of light in air. The speed of light in air is a little bit slower, but the speed of light in other materials is considerably slower. Like in water, it's 33% slower than in a vacuum. And in glass, it's typically about 50% slower. Well, it's called the refractive index, which is the ratio of the speed of light in a vacuum compared to the speed of light in the material. So for glass, it's between 1.5 and 1.7 usually. So that means that when light is going through glass, it's not going at its full speed of light speed. It's going at 1.5 times slower than that speed. Why does that happen? The reason it happens is that in something like glass, the light is continually getting absorbed by an atom, re-emitted by the atom. So what happens is the light hits an atom, it makes the atom, it puts the atom in a new state where the atom says, I just absorbed a photon of light. It takes the atom just a little bit of time to re-emit that photon of light. And so it's like it's playing some kind of relay type thing where the light is falling on one atom, takes the atom a little bit of time to emit that light again, and keeps going. And that's how light gets transmitted through something like glass. And that's why the light is not going at the official speed of light in glass. But anyway, so the ping times on the internet are roughly determined by the speed of light in glass. Now, that's not the whole story, because what happens is it's not just going through this one cable. It also has to go through electronics that tell it which cable to go through and figure out how to switch things and so on. And actually, a lot of the time that's taken in communicating between computers is actually inside that switching stuff rather than the actual transmission along the fibers. But the actual transmission along the fibers does take some time, and you can detect that as you look at websites that are further away from you physically. You'll find that it takes longer to the ping times will tend to get longer. All right. There's a question here. Can you ask about the coronavirus or only about science? I can talk about the coronavirus, what I know about it. Okay. Oh boy, we're going to. So somebody's got to ask the question, what is spin? Let me avoid talking about that question. I'm happy to talk about that sometime, but shall I try it? All right, I'll try it. Okay. Okay. You want me to tell you what it actually is? I'll tell you just because it's fun to hear the words. So a particle, like an electron, has each electron has a certain mass. All electrons have the same mass. And the official definition of spin It is which irreducible representation of the Poincare group does the electron transform according. I can use all the fancy words. I'm not going to use these fancy words because this is absolutely useless. Let me try and explain. So, in a sense, those fancy words tell us that spin is something that is sort of understood in terms of mathematics and in terms of fairly abstract concepts. So I have a guess about what spin really is in terms of the way that space is built and so on. I don't yet know if it's completely correct, but let me tell you kind of the standard, well, let me tell you a mixture of kind of what spin is. So roughly, you can have an object, let's say, I don't know, if you know, like a top can be spinning around, right? Top spins around. And one of the things that happens with a top is it just likes to keep on spinning just the way it's been spinning. And that's similar to if you throw something, it will tend to keep going in the direction that you threw it, at least until gravity makes it turn in a different direction. So the reason it does that, one way to explain that is its conservation of linear momentum. There's this idea of momentum when things are moving. The mass and velocity combined together make momentum, and so a massive object going in some direction will tend to keep going in that direction. In physics, there's a conservation of momentum. So things starts going in that direction, it will keep going in that direction. Okay, so that's linear momentum. There's also a conservation of angular momentum. When you start something spinning, it will tend to keep on spinning. Okay, if you have a top, for example, the top will eventually stop spinning. And the reason for that is there's friction. If the top is just spinning on a little point, there's friction between that will tend to slow down. Friction, for example, between the point and the table, or friction because the top is moving in the air, that will tend to slow the top down. But if there wasn't any friction, if you had this top spinning in space, then the thing would just keep spinning around. It would keep spinning kind of forever. That's conservation of angular momentum. Okay, I have to tell you a story. A friend of mine who's an astronaut, used to be an astronaut, had an experience with spin in space that was one of these figure out physics in real time kinds of experiences. So he was on the space station called Mir, which was a Russian space station, was a predecessor of the current International Space Station. He was on the space station, and the space station was, there was some accident on the space station, and that caused the space station to start rotating, to start spinning. And in fact, because there wasn't any air to slow it down, there was nothing to slow it down, the space station just kept on spinning. And so it was a big question, how should they stop the space station spinning? And in fact, my friend used our Mathematica program to figure out, and you have to be a very kind of cool cucumber of an astronaut to be hanging out in a space station that's spinning around, and to get out your computer and start writing down differential equations and solve the equations and things and figure out, yes, if we fire this thruster in this direction, then we'll stop the space station spinning. But he succeeded in doing that and figured out just by using the math equations how to stop that space station spinning. And then, of course, the story would be much better if he'd been able to implement what he figured out and that had worked. But in fact, the Russian ground controllers who were in charge of what happened to their space station were like, no, you can't do that. That's not our procedure. We have a procedure for what to do. Well, we don't know exactly what it is, but anyway, after a day or so, they managed to use some other procedure. But it was kind of a shame that the differential equations for solved in real time to stop the spinning space station never actually got able to be implemented. But in any case, so in large scale objects, there's this idea of angular momentum, and there's a conservation of angular momentum. Okay, when you have a very small object like an electron, electrons also spin around. But when you have a big object like a space station, you can make it spin faster or you can make it spin slower. When you have an object like an electron, for reasons that we don't yet fully understand, you can effectively only give it one particular amount of angular momentum. So all electrons have, in the units of angular momentum that's used for electrons, they have half a unit of angular momentum. So all electrons have half a unit of angular momentum. They can actually be, essentially, they can be either plus half a unit or minus half a unit. That whole story is a little bit complicated with quantum mechanics, but roughly, I think it's fair to say an electron has half a unit of angular momentum. A proton also has half a unit of angular momentum. Photons have 1 unit of angular momentum. Gravitons, the particles that make up gravity waves, they have 2 units of angular momentum. And the number of units of angular momentum that a particle has a big effect on how the particle works. And the most important effect is if you have an integer number, a whole number of units of angular momentum, you're a thing called a boson. If you have half integer number of units of angular momentum, you're a thing called a fermion. Okay, what's the difference? What's the big difference between bosons and fermions? Basically, bosons are super social and like to clump together, and fermions are kind of super antisocial and like to stay apart. Okay, why do we care? Well, the reason we care about fermions staying apart, like things like electrons and protons and so on, is that most matter that we deal with, atoms and things, are made of fermions. And the fact that they like to stay apart is what causes matter to not all collapse. So there's a thing called the exclusion principle that basically says when you have fermions, things like electrons, things with half integer spin, they will never want to be sort of all stuck together in the same place. They'll always want to be sort of forced apart. And that's it's a large part of what leads to the stability of matter, that leads to having actual objects that don't sort of just collapse. Okay, so that's what happens with half integer spin things. With whole integer spin things, and I mentioned that photons have spin 1. Photons are examples of bosons. Photons are the particles of light. They're examples of bosons. And bosons have the property that if you have one boson, it really wants to have other bosons be right there in the same state, right on top of it. Okay, so you might say, well, so what? Well, the main so what of that is that's how lasers work. Lasers, the word laser stands for light amplification by stimulated emission of radiation. And what's happening there is that in a laser, you're trying to get lots of photons to all be in exactly the same state, all going in exactly the same direction, all shine out of the front of the laser, so to speak. And it's because photons are bosons that it's possible to, these electrons really like kind of clumping together and all being in the same state and all making this coherent laser light that you produce in a laser. So these two, so the spin is this property of particles that has to do with angular momentum, and it really matters whether things have half a unit of spin or 1 unit of spin. And that's a very, well, if you study theoretical physics in graduate school, you might hear about a thing called the spin statistics theorem, which is the piece of mathematics that shows that there's a connection between the spin of a particle and whether it wants to be clumped together or stay apart. I could mention one more thing about that, which might be too complicated, but well, okay, just a thing, if you're curious, you can look up. There are things called spinors. And normally, when we have something in ordinary three-dimensional space and we rotate it around, we rotate 180 degrees, it's backwards. We rotate it 360 degrees, it comes back to where it started from again. Okay? Turns out for things like electrons, they don't work that way. They actually, when you turn them around by 360 degrees, they don't come back to where they started from. You need to turn them around by 720 degrees. You need to turn them around essentially 2 full revolutions before they come back to where they started from again. And that's a weird and interesting phenomenon that I could talk about some other time. Okay, let's see. Okay, there's a question here. Boy, you guys are asking about physics a lot. Let me see. Gosh, lots of great questions here. what should I try and take here? I've been talking a bunch about physics. Let me try and talk a little bit about math, since there's a question here about math. It's a question about statistics. Let me see. All right. Let's talk about statistics. Well, I think for that, I have to get my, actually do something with the computer. Let me do that. Hold on a second here. Okay. All right. Let's see what we can do with statistics. All right, let me, I'm kind of looking at my screen here, so I might be looking up in a rather strange angle, but sorry about that. Okay, well, where should we start? I think a good place to start is talking about averages. So if we say, let's say we make, I'm going to make a bunch of, I'm going to make 50 numbers between, let's make them between 1 and 10. I mean, 50 random numbers between 1 and 10. So one question you might ask is, what's the average of those numbers? So let's say, for example, those are, I don't know, distances you throw a ball or something like that. You could say, what's the average of those numbers? And so there are various ways to work out that average. Maybe, actually, let me do something slightly different here. Let me make my random numbers a slightly different way. Let me say this. Oops, that's not what I wanted. Sorry. Okay, so here I've got a bunch of numbers, and I want to say, what's the average of these numbers? Okay, so one convenient thing to try to do is to make histogram. So a histogram, let me just make it here. So a histogram says, let's put these numbers in buckets. Let's say, how many numbers are there between 0 and 2? How many numbers are there between 2 and 4? How many numbers are there between 4 and 6? So this is saying, for each bucket, like this is the numbers between 0 and 2, this is saying that, I can't read this off here, but there are maybe 16 numbers between 0 and 2, same 16 numbers between 2 and 4, some, I don't know how many it is, 6 numbers between 4 and 6, and so on, okay? So we have numbers in these various buckets. And so this histogram, we can say, if we want to say, given these numbers, what's the chance, if we were to pick, okay, let's imagine that we wanted to say, what's the chance that one of these numbers is between, let's say, 0 and 4? What we'd have to say is, how much stuff is there that falls between, in these buckets between 0 and 4 compared to all the other stuff? And that will give us the, so let's imagine, let me give a slightly different example, but let me keep going on this. Let me show you, let's say, let me do a few more of these. Let's say we do 500 of those, and let me make the same histogram again. So I'm just using, so now I'm going to ask the question, let's imagine that this is heights of different, what's about that height? I don't know, pet grasshoppers that are different. No, I don't think they're negative height pet grasshoppers. Bad idea. What could this be? This could be the distance a snail walks towards a piece of lettuce in a few minutes. And sometimes the snail walks backwards, so it's a negative number. Okay, but anyway, so now we want to ask something like, what's the average distance that the snail walks towards the lettuce? And so how do we work that out from this? Well, what do we think the average is? Well, we might say, if we were to cut this out as a piece of paper and we were to try to balance it, we would say, where would we put the balance that would make it be sort of an equal amount of paper to the right and to the left? So that's one way that we could sort of decide what's the middle of this. What do we count as the average of this set of distances the snail might go? And that way of working things out is called the mean of the distribution. Another thing we might do is we might say, I want to say, let's make sure that half of the this may be not the best way to explain it. I think I should have. So there are these different kinds of averages. There's mean, median, mode. So the mode is an easy one to explain. The mode is what's the most likely value. So that would be this bucket here. So there are these different kinds of averages, but in general, this so like this might be a distribution. It's the same shape distribution. There's a very common shape of distribution. It's called a normal distribution or Gaussian distribution or bell curve sometimes, and a lot of things follow that distribution. So for example, for human heights, they follow that distribution. For any given age, etc., if you work out what's the distribution of heights. I mean, I'm sure I can do this if I pull up Wolfram Alpha. Let me do that. Hold on here. Okay, here we go. Let's say I don't know, girl age 12 height. So, and you can do this with Siri and things like that, which are powered by Wolfram Alpha. I'm pretty sure they give you this information. Oh, that's not good. Let's ask it. Let's say, oh, I see. That's what we want. Okay, there we go. So this tells us for girls age 12, this tells us if we looked at lots and lots of kids, this shows us the distribution of their heights. So it tells us the most probable height seems to be, well, it's a little bit under 5 feet here. And this tells us this tells us what the distribution of heights is. So if you were to have a bunch of kids and you were to measure all their heights and you were to put them in bins of, you know, who is between this number of inches and that number of inches, the number of kids would correspond to the different bins here. So that's the distribution of human heights. So for example, you might say, let's say you are, you know, 4 foot 5 inches tall. You might say, oh boy, that makes me really weird. I must be, you know, there must be so few people who are my height. Okay, this curve tells you how many people are less tall than you are and more tall than you are. All you have to do is work out the area under this curve. So the number of people who are less tall than you are, if you're 4 foot 5 inches tall, the number of people less tall than you are is the number of people in this tail here, and the number of people taller than you is the total number, is the total area above you. And so when so for example, this actually says the 95% range corresponds to 4 foot 5 to 5 feet 5, 4 foot 5.6 inches. So what that's saying is 95% of people, 95% of girls age 12 are between 4 foot 5.6 inches and 5 foot 5.3 inches tall. Okay, and you can read that off from this distribution. That's telling you the area, 95% of the area, 95% of the, if you pick a kid at random, then 95% of the time they will be between this height and this height. And about 5% of the time they'll either be shorter than that or taller than that. Okay, so you might ask, I mean, not all things are distributed like this. So for example, I know we have a plot here, the weight distribution. Human weights have a different distribution. They actually have a thing that's called the log normal distribution, roughly. So that means that there are there's a tail here where there are people who are larger and heavier, and there are more of those than there are people who are lighter. So it's a slightly different setup. And if you look at different kinds of things, these distributions, you get different kinds of distributions. So for example, if we look at, I don't know, if we look in the stock market at the prices of stocks, their prices bounce around. I don't know, let's pick a company. Let's see, how about Apple? Let's see what's been happening with them. So that's their, oh, poor Apple. That's their stock price. And this is showing the distribution. This is showing what their, the middle is their average stock price. And this is showing how their stock price differs. What the chance is that you will find a price, if you look at different days or different hours of the day, that is 10% higher, 19% lower, and so on. And so this, it's again, this distribution is roughly, for stocks, very roughly, also a normal distribution. Although stocks tend to have tails, and there are all sorts of terrible things that happen. So for example, the distribution might say, well, gosh, you can go down to have, there's a certain probability to have a negative stock price, but actually there can't be a negative stock price. The company wouldn't be in business if there was a negative stock price. So that means it can't be exactly that distribution. But so that's a little bit of a micro introduction to a little bit of statistical stuff. So one thing that happens, like when people talk about medical tests, and they say things like, they talk about p-values, and they talk about, you know, this test works X% of the time, and so on, or the value of this thing is such and such with a 95% confidence interval. A 95% confidence interval just means that the distribution, 95% of the time, the values will lie between what is, if you say the value of this thing is between -2 and 4 with 95% confidence interval, it's saying that 95% of the area of the statistical distribution lies between -2 and 4. Now, unfortunately, because I think one might say, because people who are, you know, racing to do frontline medicine and so on don't always know or learn as much math as they might, sometimes that gets a little bit messed up, and people end up quoting these kinds of things, like these things called p-values. They quote them and they say it's this value to this value based on some experimental data, and they assume that it follows one of these normal distributions, and actually it just doesn't. So that leads to some things that are kind of hard to figure out. And it's usually better to look at the actual distribution. So for example, if we look at, what's a good example? Let's see, what would be an example of, well, for the old folk, let's see, let's say, okay, this is more for the parent crowd. If you measure, this is cholesterol, measure cholesterol in a male age 40, again, you get one of these distributions. This is telling you what the chances are. This says the most likely, okay, so this is saying 95% of males age 40, if you measure their LDL cholesterol level, it will lie between 65 and 200. So, and this 1 sigma means 68% lie between 92 and 161 of these units. So there's another one of these distributions. And a lot of the time people will quote, oh, you have a normal cholesterol level. Okay, what does that actually mean? Well, it often means that you lie within the 95% confidence interval. Sometimes it means you lie within the 68%, the 1 sigma confidence level, and so on. Anyway, that was a really micro introduction to some things in statistics. Statistics is a big subject, and I'm really not doing it justice here, but that was just a little sort of micro discussion there. All right, let me go back to our stream here, if I can work this properly. Let's see. All right. Okay, so there's a question here about, did humans evolve from monkeys? Okay, so the first statement to make is there's this whole phenomenon of evolution. There's this whole tree of life that's existed on Earth. And maybe it started, I don't know, 2.5 billion years ago, maybe, that the first living organisms existed. And ever since then, we've been, even from the very beginning, probably, well, probably not the very, very first living organisms, but fairly soon, DNA, this molecule that is essentially gives us the program that specifies how to build an organism. Pretty soon, organisms started using DNA to specify the program that would be used to build them. And like, you know, our DNA has 6 billion base pairs, essentially 6 billion, well, 6 billion times 2 bits of information that specify how to build us. And they specify how our cells should should turn our food into proteins and make everything that's us. Okay, so back in the, you know, when life first evolved on Earth, probably it didn't actually use DNA. Probably it used, I don't know, there's some theories that it used things in clay and clays and other kinds of ways to sort of keep information about how it should be built. But roughly what's happened is that over the course of time, the program for building life, for building organisms, has gradually been refined and refined and refined and refined and refined. And every time there's a new generation of organisms, their programs are a little bit different than their parents' programs. And what happens, there's this phenomenon called natural selection that was discovered in the about a century and a half ago now, by Charles Darwin, and with various input from other people. But again, don't get me started. I'm talking about history of science. I can give you a long discussion about that. But let's stick to the point. So, what is natural selection? So each organism is specified by a program. The children of the organism get programs that differ just a little bit from the programs of their parents. In the case of us humans and organisms that have sexual reproduction, we always get a mixture of the programs from our mother and our father. And so, like with humans, we have 23 chromosomes, and each one of those, there'll be stretches that are your father's DNA, your mother's DNA, and so on. They're usually about, I think it's 5 or 6 crossovers per chromosome. So you'll get, you know, if you have siblings, for example, you'll be able to see, oh, that section of chromosome 5, we both got that from our father, for example. And then it will cross over and you'll get it from the other parent and so on. Because the program on the DNA is so jumbled up, it's not the case. It's not a well-organized program, so to speak. So you're like the piece of the program that might encode how, you know, eye color, how one part of our eye color works, maybe on a completely different chromosome from the part that encodes how another part of our eye color works. And so it's not the case that just because, you know, you have sort of sections of DNA that come from one parent or another, it doesn't mean that the traits are necessarily very correlated. But in any case, so different organisms gradually, as you compared to your parents have slightly different DNA. One reason for that is because of this phenomenon of the mixing of DNA from sexual reproduction. Another feature is that when DNA is replicated, there are some errors in replication, and those errors, some of those errors are corrected by proofreading enzymes and things, but some are not. And so each of us probably has about 700,000 unique base pairs, unique places on our DNA that nobody else got, that they're just completely unique to us. Okay, so then what happens? Well, over the course of time, some of those unique mutations, some of those mutations will turn out to be a really good idea. So for example, I don't know, let's pick, let's not go for humans. Let's go for the classic thing that Darwin studied, which was a type of bird that had different shapes of beak. And he looked at birds on the Galapagos Islands, and the different islands there. And on some islands, there was, what was it? Some kinds of seeds, I guess, that existed, where if you had a particular shape of beak, you'd be more successful at cracking open that seed. I may have that slightly wrong, what the actual different functionalities of these birds is, but it's roughly that. And that's certainly one can imagine. So, if you have a beak of a certain shape, it's going to be really good for cracking open that seed. Okay, if you have that shape of beak, you will be a more successful bird. You will live longer. You will have more children. And so what then happens is that this process of natural selection, of selecting out birds that aren't so successful and selecting in birds that are successful, as that continues through generations, you'll tend to get evolution towards, for example, a bird that has a beak that's really optimized for what it's trying to do. Now, natural selection and evolution can be good and it can be kind of bad. And so, for example, one case where it's bad is in things like viruses. They have natural selection and evolution as well. Well, let me give you the example of bacteria. So one bad example there is antibiotic-resistant bacteria. So bacteria we have antibiotics. Antibiotics kill bacteria, but so if you're a bacterium and you're reproducing and you're in a place where there are a bunch of antibiotics and antibiotics kill you, then you won't reproduce. But if you suddenly, by some mutation, manage to be a bacterium that survives the antibiotics, then you'll be the winning bacterium and you'll reproduce and there'll be lots of copies of you. And so that's the thing that happens, is that the antibiotic will provide will select for bacteria that aren't killed by the antibiotic, and so you'll evolve bacteria that are antibiotic resistant in that case. Okay, so in the history of life on Earth, we have evolved all kinds of different life forms that are successful in different places. So, for example, there's life that lives in volcanoes. There's life that lives, we actually don't know how far down life lives inside the Earth, but there's life that lives deeper inside the Earth. We don't know quite how deep. There's life that lives in very cold places, very hot places, places with this feature, that feature. And those different forms of life, the ones that survive and that are naturally selected for, are the ones that, because of mutations, ended up being successful in those particular environments. Well, back in the time of Charles Darwin, he actually thought that it was a sort of feature of natural selection that it would force one to have more and more complex organisms with more and more elaborate features over the course of time. That turns out not to be true. It is not the case that more elaborate organisms are always more successful organisms. I mean, in the situation we're in right now, it'd be really good if that was definitively true, because we're significantly more complex organisms than this nasty virus that's attacking us. For example, we have, it's not a great measure of this, but we have 6 billion base pairs. For a human, the virus has 29,000 base pairs, very tiny compared to us. So Darwin thought that gradually life would get more and more complex, and that the more successful forms of life would be more complex. That doesn't seem to be the case. You can have quite successful life forms that are quite simple. So then one of the questions is, so another question is sort of what evolves from what, and are we the best life forms that have ever evolved, and how do you measure that, and how do you think about that? I think the specific question here was, do we evolve from monkeys? Okay, so first question is, how would you tell? So the way that people used to tell what evolved from what is to just look at the organisms and say, gosh, that, humans look quite a lot like monkeys, zebras look quite a lot like horses, et cetera, et cetera, et cetera. And they tried to arrange the tree of life just based on what organisms look like. And there are about roughly 10 million species that are known now, a large fraction of which are things like beetles that exist in the Amazon rainforest, things like that. But anyway, there are quite few mammalian species now, and I think, how many are there? Maybe 10,000, maybe less than that, mammalian species that are known. It's a quite small number. But in any case, of all these different species that are known, well, we have, so you can try and group them together. You can try and sort of reconstruct this tree of life of what evolved from what by just looking at what looks similar to what. And so one of the things that has been observed is there are fossils which show what organisms that have existed in the past looked like. And so we can try and piece together what was the kind of historical tree of life by piecing together, well, this fossil looks like this one and looks like this one, and we can try and make a chain going all the way back. And sometimes, a lot of fossils, we can make those kinds of chains. There are some wonderful fossils, like from the Cambrian period, let's see, a couple, 200-300 million years ago, I think, that there are fossils from well, actually the Precambrian period, where they're really weird-looking organisms that don't look anything like the organisms we have today. They were kind of things that, in a sense, evolution tried out, and they turned out not to be very good ideas, or at least for whatever historical accidental reason, they didn't make it. So, for example, just like we have 5 fingers, and there are a lot of organisms that have 5-fold symmetry, there were organisms at that time that had 7-fold symmetry and all kinds of other things. And for whatever reason, the 5-folders won out. Okay, so one way that we can tell kind of what evolved from what is just to look at the shapes of the organisms and try and sort of piece it together. Another thing that's become possible more recently is to look at the DNA sequences, the programs for these organisms, at least the ones that exist today. Sometimes we can get some DNA from ancient organisms. There's sort of a hope we might get, there's good science fiction from getting dinosaur DNA and things like this. That hasn't been successfully got yet, but it might be possible. But we can also just try and deduce from, if we know the DNA of this organism looked like this, and we know it's a small change from the program of one organism to the program of the organism that was the result of a bunch of mutations from that organism, we can kind of try and piece together this tree of life also by looking at the level of programs. So people have tried to do that for humans. I'm not a huge expert on all the things that have been found, but it's clear that there were a bunch of species that existed a couple of million years ago. I think modern humans are maybe 50,000 years old or something. But there were a bunch of species that existed, and they had different characteristics. Some of them probably only went extinct. I think there's one Homo florensis that I think may have existed until 500 years ago. There's a very kind of hobbit-sized human-like organism that and there were also Neanderthals, which were a different species, the Denisovans, which were another species. I think there's actually very recently, the last couple of months, there's a discovery in Africa of probably signs of yet another species. And all these different species were pretty similar, and they interbred. And in fact, for example, for us, like we have signatures of the Neanderthal species, for example, in us. I think blue eyes, for example, I think are one of the contributions of the Neanderthals to modern humans and so on. So we can kind of try and piece together what came from different species and how that worked. But so that's, and it's always a question of when there were particular sort of innovations that were made in history, like, what species first had language? What species first made art? And that's a thing that's actually pretty actively discussed these days. Of did the Neanderthals make art? Did they have, what kind of language did they have? It's often hard to tell. You can look at the vocal tracts and things like that, the structures inside the kind of the throats and things and skeletons of these organisms, and you can try and guess, did they have the kind of thing it would take to have to make different sounds and so on. I'm not sure that's a totally convincing way to do it. If you're lucky, you'll find a cave painting or something, or an artifact. It's even, that's a hard business too, because the artifacts that we find, like flint knapping, one of those things that I suppose got taught in school back 10,000 years ago, but it's kind of been lost since then. It's like, how do you take a flint piece of rock, and you just keep knock on the flint, and eventually you can make it sharp. And that's a good thing if you're trying to make an arrowhead. And so back in the day, in ancient history of our species, that was a super useful skill, is how to make sharp points out of flints. But if you find an arrowhead that was made with flint knapping, it's pretty hard to tell. that we know how flint knapping works because kind of flint knapping sort of survived until modern times. But if we found some rock that was, seemed to be chipped away in some weird shape, to know that that was something that was done purposefully by some distant ancestor of ours is a tough thing. It's a tough thing to know. Did they, like we know from archaeology and things like that. We know when we look at sort of ancient monuments, we say, what was this for? And it's often hard to tell. All right, let's see. Gosh, let me look at some of these. This is one I don't know the answer to. I'm sorry. I'll tell you the question, but I don't know the answer. It says, why does an egg turn into rubber when put in vinegar? Well, I know it doesn't actually turn into rubber, but it may turn into a rubbery substance. I can guess the answer. An egg has protein in it, and proteins are very long, long molecules. And and the kind of the consistency of these long molecules, and that's how rubber works actually, is affected by how far these molecules are kept apart. But I'm sort of guessing here, so let me not. I'm sorry, I don't know the answer to that. All right, there's a question here. Is there a maximum temperature? Okay, that one I can answer. Okay, so let's talk about what temperature is. I actually talked about that in the last one of these a little bit. So when you have a bunch of atoms, temperature is basically the energy with which those atoms are bouncing around, roughly the speed with which the atoms are bouncing around. So in air, let's take water. In steam, the atoms are running around really pretty fast. It's a gas. You cool it down, the atoms are running around a bit slower, and they're kind of being stuck together a bit, and that makes liquid water. If you cool the atoms down even further, they'll tend to not run around very much at all, and they'll be kind of locked in place, and that makes solid ice. Okay, so temperature it's actually the average kinetic energy, the average energy of motion of the atoms or molecules in a substance, and or whatever is making up the substance. So temperature is associated with these microscopic motions in a material, and so that means there's an absolute zero, a minimum temperature, because there's a temperature at which you've taken all of that energy of motion out, and the atoms are just staying completely still. And so I think I mentioned last time, so that means most materials turn into solids when you take them down to absolute zero of temperature. Absolute zero is minus 273.16 degrees centigrade. So it's very cold. And for example, for example, when you cool air down, air, with mostly nitrogen and oxygen, becomes minus 170 degrees centigrade. Is that right? I have to look that up. I think that's the temperature at which air becomes liquid. Let's see, 77 kelvins, I think. Is that right? No, I'm forgetting. Sorry. I have to look that up. I can type it into Wolfram Alpha and look that up. Okay, so there's a temperature at which air becomes liquid. There's a temperature below that at which air becomes solid. Those temperatures correspond to the molecules getting slower and slower and slower. Okay? All right, is there a maximum temperature? Okay, so, well, when you heat stuff up, what's going to happen? The molecules are going to go faster and faster and faster. Boy, this is actually tricky. This is graduate level physics. Sorry, okay. So what you put more and more energy into these atoms. Well, first of all, as you put too much energy in, the atoms will fall apart. And it'll just be because when the atoms are held together by a certain amount of force, and when you put in too much temperature, the atoms are sort of torn apart. It's what happens in fire and things like that. It makes a plasma where the electrons are torn out of the atoms. Okay, but when you make things hot enough, everything gets torn apart. Even atomic nuclei get torn apart. When you make things even hotter, even the quarks and gluons inside protons and things get sort of torn apart. But so when everything is really, really hot, things get torn apart. But these particles, electrons, whatever they are, quarks, whatever, they can just keep going, and you can just pump more and more and more energy into those particles. So actually, in the usual theory of physics, there is not a maximum temperature. You can just keep on pumping more and more and more energy into particles. There used to be a theory that there was a maximum temperature, and that came about, let's see how to explain this. Okay, basically the idea was, we know about protons and neutrons and electrons, but they're actually a whole zoo of other kinds of particles. Most of those particles are unstable. They decay in millionths of a second or trillionths of a second or trillionths of a second. Most of them are unstable, but there's a whole giant zoo of other particles. They have names like the sigma hyperon, the lambda hyperon, the cascade hyperon, the kaon, the pion, the F meson, the G meson. There's a whole giant zoo of these things. But when I was a kid, I was really into these kinds of particles, and I used to know all about these things. I have a decent memory, so I still remember, the masses and properties of a bunch of these particles. It's a little bit, they've been measured vastly more accurately than they were known when I was a kid. But in any case, there's a whole zoo of these particles, okay? And it used to be thought that maybe as you increase the temperature of something, instead of the energy going into producing making particles go faster, instead that energy would go into producing more kinds of particles. And actually, if you've heard of string theory, one of the kind of mathematical theories that's thought about a bit in fundamental physics, string theory, the original version of string theory, came out of a theory of particles in which there were just a whole zoo of more and more and more and more particles. So it used to be thought at one time that there was a maximum possible temperature at which you would be producing new kinds of particles rather than the same kinds of particles going faster. That theory turns out not to be correct. It's an interesting question whether, in my theory of physics, whether there is ultimately a maximum temperature. What is the answer to that? The answer is that there will be. Let's see. Yes, actually, okay. Let me answer two different related questions here. So one place where things got really hot was in the very early universe. When the universe was just started, there was this big bang. Nobody knows why that happened, but there's a sort of giant explosion that started the universe. And when the universe was very small and very young, it was also very hot. And as time has gone on, the universe has cooled down, and it's cooled down, it's cooled down. At this point, the sort of, if you just go into space, space is not at an absolute zero of temperature. Space is at about 3 degrees Kelvin, 3 kelvins, which is minus 270 degrees centigrade, 3 degrees above absolute zero. That's the effective temperature of space. And the reason it's not at absolute zero is that it still has sort of the remnants of the heat that came from the Big Bang at the beginning of the universe is still there in essentially the photons, the microwave, the radio energy in the universe. That's still sort of a relic of the Big Bang, although by now, because the universe has expanded a lot, it's really cooled down, so it's only 3 degrees above absolute zero. But in the very early universe, the universe was really, really, really hot. In fact, probably in some sense infinitely hot. Now you're going to ask me to do some kind of advanced physics in real time of physics theory that is not yet fully developed. But I think in my theory of fundamental physics, there is a maximum temperature. And I think that maximum temperature, let me think about this for a second. Yes, yes, there will be a maximum temperature, and it will be, let's see. The reason there's a maximum temperature, I mean, the maximum temperature will be unbelievably huge compared to anything that we can observe in the universe, with the possible exception that at the edge of a black hole, one might see some phenomenon associated with that. I have to think about that. That is a good question. Thank you. That's my homework, I think, is to figure out in my theory of how space-time works, how maximum temperature works. So somebody who's paying attention to the live stream from my team, take a note of that. That's my homework. Let's see. Let's see. Okay, here's another question. Is there a maximum location accuracy for a GPS system? Okay. First of all, let me explain again a little bit about how GPS works. GPS, the Global Positioning System, that's an American network of satellites, and there's actually a European one and there's a Russian one, I think. But the GPS is the most commonly used one. Okay. So one big question is, how do you know where you are on the Earth? That was a big issue when people were, particularly on the oceans. If you were trying to figure out where am I, and I'm, near my house or something, it's like, oh, I know that. That's, I recognize that landmark. But on the ocean, there aren't any landmarks to recognize. So it's much harder to tell where you are. And so so the main way that people used to tell where they were is by navigating by the stars. And the reason that will tell you where you are is the stars, as the Earth rotates, the stars will be at particular, the stars stay at a fixed location. And as the Earth turns, you can basically see where the stars are. Now, it turns out that if you are to know your latitude, that is how far you are from the North Pole or from the equator, how far north you are, basically, that's something you can figure out just from angles of stars as the Earth turns. You know where the North Star is, which is roughly aligned with the North Pole, and you can figure out by seeing what angle the Polaris, the North Pole star is at, or a corresponding thing in the Southern Hemisphere, you can figure out what latitude you're at. It was a big problem for many years to figure out the longitude, because to work out longitude, you have to know what time it is. You have to know, this star is overhead. Okay, great. But what time does that correspond to? And so there's a big issue of how you can get an accurate enough clock to be able to know what time it is. And so there was this big thing to create a marine chronometer. And the big issue is clocks used to be, well, they were made with pendulums, which swung back and forth, or they're made with escapements, I guess, these sort of springs but essentially it's little pendulum type things. And the problem is, if you're in a ship and it's on an ocean and you're being thrown around all over the place, it's really hard to get the clock to keep accurate time. And so people invented these whole elaborate systems to kind of keep the clock from being bounced around too much in the ocean and keeping accurate time. And eventually that problem was solved. But that was the early system for navigation. Okay, so then when airplanes started flying, there was a need for navigation for planes. For planes, there's a different scheme that was used. For planes, there are radio navigation beacons. In the US, they're usually called Vortex, VHF, omnidirectional radio beacons. And the way they work, they're kind of clever, actually. You can see them sometimes. You can see them. They're often near airports. Sometimes they're sort of on hillsides and things. They're kind of these things that have they usually have this kind of shape. They're radio beacons, and they produce so if you're flying a plane, you before there was GPS, you would try and get a fix on a radio beacon, and you would say, this radio beacon is at this angle to me. And actually, these radio beacons have a clever feature that they actually had two different radio frequencies. And as you go around a circle around that radio beacon, the relative, these two relative frequencies would change as you go around the circle just by the construction of the radio antenna in the radio beacon. And so that allowed you to tell what angle were you at relative to that radio beacon. And that was a method of navigation that was used. In fact, still the airplanes, you might think airplanes can go anywhere in the sky, but actually they tend to follow these particular sort of airways, which typically are flying from one radio beacon to the next radio beacon in straight lines. Eventually, it's going to get figured out how to let planes use GPS and take arbitrary paths, and that will save some fuel and other good things. But in any case, so that was another scheme. And then GPS was invented, and GPS is a different idea. GPS is using satellites. And okay, so how does GPS work? Basically, the satellites, so first fact is, once you put a satellite in orbit, you can compute just with math really pretty accurately where that satellite will be at every moment. And so, if you type into Wolfram Alpha the name of some satellite or the International Space Station or something, it will predict for you where the International Space Station is going to be 3 days from now. And it can do that quite accurately because the physics of orbits and things is such that you just work out these equations, differential equations, and they tell you, sometimes they're kind of complicated, but they tell you just by math where the thing will be. Now, the math all breaks down if your thing fires a little rocket thruster, then you can make it change its orbit. But assuming it fired no thrusters, assuming it didn't hit the upper atmosphere, hit the top of the atmosphere and start getting slowed down by that, assuming none of those weird things happened, you can, just by physics and math, you can predict where the thing will be to really very high accuracy. Okay, so there are these GPS satellites, and they're orbiting the Earth, and you can predict where any one of those satellites will be. Okay, so then if you want to know where you are, you have to say, well, how far away am I from those satellites? So if you want to work out, if you say, where am I? If I'm somewhere on a line, and I know I'm this distance from one end of the line, then I know where I am on that line. And if I want to work out if I knew in 2 dimensions, if I knew I was somewhere on a flat plane, and I know I'm this distance from one, I know I'm this distance from, let's say I know I'm 10 miles away. Well, let's be more realistic. Let's say I'm 1,000 miles away from this point on the plane. Well, what points are 1,000 miles away from this point? The answer is it's a circle. The set of points that are 1,000 miles away is a circle with a radius of 1,000 miles around that point. Okay, so let's say I now know I'm 1,000 miles away from that point, and I'm 800 miles away from this other point over here. Okay, so where am I? If I know that I'm 1,000 miles away from this, I know I'm somewhere on the circle around that point. I'm 800 miles away from this. I know I'm somewhere on the circle 800 with radius 800 miles around that point. Okay, so I've got these 2 circles, and that means that with these 2 circles, if I want to know, if I know I'm 1,000 miles away from this one, 800 miles away from this one, I can work out where I can be. The answer is I must be on the circle around this point and the circle around this point. And so I must be on the intersection of those 2 circles. So if you have 2 circles, generically, they will intersect in 2 points. Okay, so just from knowing how far away you are from 2 things, you can work out, at least between 2 points, you can say, where am I relative to those circles? Well, if you want to break the ambiguity of those 2 points, you need a third fix. You need to know the distance to a third point. And given those 3 points, you can work out where am I exactly. So that's kind of the idea that GPS uses. It tries to work out how far away are you from 3 satellites. Usually it's 5 satellites or more that actually get used in a typical GPS receiver. And somebody's asking, how far away am I from the GPS satellites? All right, let me let me ask Wolfram Alpha here, class of satellites. It'll give me the, if we type this in here, I'll just show you. Hold on, let me just bring this up. Okay, I just typed in GPS into Wolfram Alpha. This is showing me apparently there are 39 GPS satellites, and okay, so this is telling me the all kinds of details of the GPS satellites. So it's telling me that the transmission delay from me to the GPS satellite is 186 milliseconds round trip to that GPS satellite. So if I pick one of these GPS satellites, I'm sure I can get a picture somewhere here of where all the GPS satellites are. But let's pick Navstar 2A-12. Let's see whether it knows where that satellite is. Oh, it's probably computing it busily here. Okay, that satellite is currently over the Southern Ocean, Southern Indian Ocean. It is 13,000 miles altitude. The transmission delay is 224 milliseconds. The satellite is going at, that's actually interesting, instantaneous. Oh, that's because it's not in low Earth orbit. Okay, this confused me because a satellite in low Earth orbit is always going at 17,000 miles an hour, but this is not so low to the Earth. Yeah, it says it's medium Earth orbit. Okay, so this is telling me that satellite was launched 1993. Okay, so it's telling me the distance to that satellite. Okay, you really want me to work it out? I can work out the actual distance to that satellite. But this is telling me the round trip time to the satellite from where I am right now. But I could work out, let's see, what is this called? Navstar 2A-12. All right, let's try typing that in. Navstar 2A-12. See if this works. He's living very dangerously here. Okay, let's try typing. I wonder whether we have a, let me just work out what this is. I need to know, actually, probably if I just say, where is it? Where is it? Where is it? I want the position. Where is it? Position. There we go. Okay. All right. This is really living dangerously, but let's do it. Okay. So this is going to tell me the position of that satellite. Okay. So that tells me right now that satellite is at latitude minus 38 degrees. That means it's in the southern hemisphere. Longitude 81 degrees. That means it's somewhere over in the east, so to speak. And this is the altitude in meters of that satellite. Okay, so let's say, where am I? I'm in Concord, Massachusetts. So let's at least get, I'm not going to give you my precise GPS coordinate, but let's just use the center of Concord, Massachusetts. So let's say the geoposition of the center of Concord, Massachusetts. And that's going to give that. Now I can work out, at least on the surface of the Earth, it's easy for me to work out the geodistance from that geoposition to the geoposition that the satellite was at when I asked the question, because the satellite, remember, is moving at 8,500 miles an hour. So it's actually going to be in a different position by now. Okay, so the satellite is about 10,000 miles from where I am right now. And we could work out, I think that might not be the slant position. If I want to get that, I can say that I am at, I think that gives us, let me see. That gives us, see, this is where things get kind of complicated. Okay, that number there is probably the distance to the center of the Earth for the position of the satellite. Let me see. 2.1 times 10 to the 7. Yes, it probably is. Okay, so what I'm going to do here, if I really want to know how far away that satellite is, I'm really going to, let's really get this right. Let's do this. And then in here, I want to say radius of Earth. Actually, I want to, whoops, I'm going to just use this quantity. Okay, this is where, how folks like me try and actually work stuff out. All right, let's see, that was the distance there. Okay, let's put that in. This is, so this is going to give my position on the Earth. And now I should be able to say geodistance from my position on the Earth to the position that the satellite had, at least when I asked for that position, which was a few minutes ago. Let's see here. And, okay. Oh, it had already worked it out correctly. Okay, it had already got that right. It was already calculating it based on me being on the surface of the Earth. So there's the answer. Okay, so the question that was actually asked here, I think, was what determines the accuracy of GPS? Okay. Boy, you guys ask complicated questions. All right. Okay, the GPS satellites. So one question is, when did your GPS receiver has to work out how far it is to each of those GPS satellites. The way it does it is actually pretty clever. The way it does it is the GPS satellite is producing a sequence of zeros and ones. It's a very particular sequence. It is a, what is it called? Shift register sequence, yeah. Let's say, oh, that might be too long. Let's do, okay. The satellite is producing a thing called a shift register sequence. And it actually is producing one of these that's millions of bits long. And one feature of this sequence, it has a very interesting mathematical property. If I were to look at some block of digits here, that block of digits only occurs once in the sequence, up to a certain length. So it's saying if I see 1001011, I know where in this sequence I am. So just by seeing the block of digits, the piece of radio pulse that I see from the GPS satellite, I know where in the sequence of the GPS satellite I am. Okay, so every GPS satellite is sending out a shift register sequence, and those sequences repeat. Let's see, the longer ones repeat every few months. I think the shorter ones repeat every day or two, maybe. But within that time interval, you can tell exactly, because it's known, every GPS receiver knows when the GPS satellites are going to generate a particular part of that sequence. So they see, oh, we saw 100100111. That means we are at this particular part of the sequence. That means we are at this particular nanosecond in time relative to when the sequence started, because the sequence is repeating, that each bit is being delivered at, takes, let's see, around a few nanoseconds, I think, corresponds to each bit. Now, actually, I mentioned earlier, the speed of light is roughly 1 foot per nanosecond. So if you can tell how long it took light to get to you from the GPS satellite to within 1 nanosecond, you can tell where you are to within 1 nanosecond. By knowing, if you can predict the orbit of the GPS satellite, so you know where the GPS satellite is, you know how far away you were from 3 GPS satellites, you know that to within a nanosecond, to within a foot, then you can triangulate to work out your position within a foot. So in principle, GPS it's really limited by how fast these bits are being transmitted, and that's limited by the radio frequency that's being used, and so on. But there are some other limitations. There are, in fact, for a long time, there was a thing called the P-mode GPS, the precision mode of GPS. And the precision mode of GPS was actually blocked for a long time because it was used for military purposes to be able to have precise homing for things. And the civilian GPS was accurate only to, I don't know what it was, 20, 30, 40 feet, something like that. Actually, during the Gulf War, was the first time that P-mode GPS was unblocked. But then a few years ago, the US Defense Department decided to open up precision GPS so everybody can use it. And that allows GPS receivers to know positions to within a few feet. And there's a thing called differential GPS, which tries to use use extra information from looking at differences between satellite signals and things to work it out even more accurately than that. So that was a long answer. You guys asked complicated questions, but I think that it was a fairly it was a fairly decent answer to the, is there a maximum location accuracy? The answer is, I believe it's ultimately limited by the frequency of these signals being sent. It is a good question whether it is limited by the accuracy with which we can predict the orbits of GPS satellites, and I'm pretty sure it's not. Pretty sure that we can predict the satellite positions to really very high accuracy there. Okay, let me see. Let me just go back here. Hold on one second. I am confusing myself. Oh, there we go. Okay, let me keep going here. I just have to rearrange my screen so I can see what questions you're asking. Okay. Is it true that all objects, including living things, emit radio waves? Oh, that's interesting. Okay. Okay. What are radio waves? Radio waves are otherwise known as electromagnetic waves. They are the result of whenever you have a charge, a piece of an electrically charged thing, like an electron. Electron is the smallest unit of electric charge. And electric currents and wires and things are made essentially from the motion of electrons. Moving electric charges through wires makes electric currents. Whenever you move, whenever you accelerate an electric charge, it will produce a radio wave. It will produce an electromagnetic wave. Now, it's a very tricky thing because there are many ways to accelerate a charge. So, for example, one thing you can do is by using voltage. Voltage is kind of the force with which you're pushing electrons through a wire, for example. And current is the number of electrons that are flowing through the wire. So as you change the voltage, you reverse the voltage, you keep reversing the voltage, you're pushing the electrons like back and forth inside an antenna. And that will cause the electrons to accelerate as they go. They're accelerating one way, then they slow down, they turn around, they accelerate the other way. Every time they accelerate, they produce electromagnetic radiation. And so anytime there's an accelerating charge, there's electromagnetic radiation. Okay, for physicists, okay, it's a slightly fancier story. Math fact, it's actually x dot x triple dot rather than x double dot squared is the actual rate of radiation, which produces some weird effects that let's not discuss here. But in any case, in a first approximation, whenever there's an accelerating electric charge, it produces electromagnetic radiation. If it is being accelerated and wiggled around at a frequency of, let's say, 1 billion sort of wiggles per second, it will produce microwaves, radio waves. If it's wiggled 1 trillion times a second, it will produce visible light. If it's wiggled even much, much faster than that, it will produce X-rays. But in general, anytime you sort of accelerate a charge, it will produce electromagnetic radiation. Okay, the question is, does that mean that there is electromagnetic radiation produced by produced in, for example, in living organisms? Usually the answer, I think, it's a good question. I mean, there's certainly an electric eel certainly succeeds in producing an electric current, and it succeeds in producing electromagnetic radiation. In kind of the, okay, so sort of tricky fact is that there are electrons that are being whizzed around atoms. Those don't normally produce electromagnetic radiation. If you, good question. Is there anything in us that in the normal state of affairs will produce electromagnetic radiation? Oh yeah. I'm sorry, I'm not thinking straight. Yes. Okay. So so the way our muscles work, okay, the way our nerves work, they're sending electrical signals. So a nerve, like we'll have a nerve fiber that will go, I don't know, up, some part of the way up our arm, then there's a repeater, and then there's another nerve fiber, it goes up to our brain, it goes to our spinal cord, then goes to our brain, and so on. Those are like little wires, and they are transmitting electric signals. And those electric signals usually they're in little pulses, maybe 1,000 times a second, and the rate of so, for example, when you touch something, the touch sensors in your fingers are producing little nerve endings that produce that use electrochemistry. They use kind of chemical processes to produce an electricity that then flows through the nerves, and then our brains detect that. And inside our brains, there's lots of nerves that are sending electric signals all around, and that's kind of what our processes of thinking consist of, is those electric signals and all the different interactions in the 100 billion or so neurons, nerve cells in our brains. So whenever we sort of, the way our muscles work is we have nerves that go from our brains, and they go on our muscles. And when an electric signal comes from our brain through the nerve, when that electric signal is applied to the muscle, there's this protein called actin, which is a long filament type protein. And when there's a little electric signal applied to that, it will tense up. And that's what causes our muscles to tense up. And so what happens is that that electric signal, so every time we are moving our, as I move my arms around or whatever, what's happening is an electric signal is going from my brain and it's causing some muscle. The electric signal goes to the actin filament in my muscle, which is then tensed up and then causes my arm to move. So that electrical signal, you can absolutely detect that. You can measure, it's usually called MEG, oh gosh, what's that stand for? In any case, you can measure electrical signals from the nerves when you tense up muscles and things like this. In fact, in our brains, you can measure the electrical signals in our brains. That's what EEG is doing, electroencephalography. And we can, in our brains, normally there's these various rhythms. The neurons in our brains tend to sort of operate in a somewhat collective way, and so there's a rhythm around 9.8 cycles per second that is the alpha rhythm of the brain, which is sort of a collective electrical effect of our neurons, which we can detect by putting little electrodes on our head. So that's and by the way, there are other electrical signals in humans, like the heart, for example, is a muscle that's pumping blood and so on, and it is when it contracts and so on, sort of the signal to tell it to contract comes from nerves that come from the brain, and you can measure that. You can also measure the electrical activity associated with the actual. Actually, you're mostly measuring in EKG. You're mostly measuring the actual muscle, the electrical effects of the actual heart muscle, I think. And that, again, is another place where us humans produce electromagnetic effects. They're very, you have to stick electrodes on yourself normally to be able to detect that. There are very sensitive. There are electrical signals that will be traveling through space, from us humans. And for example, the magnetic analog of EEG, you can effectively detect that from a distance, although you have to be in a a place with very little electromagnetic interference. Okay, I think we should wrap up soon here, but let's see other questions. Let's see. Okay, there's a request here about giving a presentation about the nature of scientific thinking. That'll be fun. Okay, something to try. All right. There's a question here. Okay, I'm going to maybe two more. I'll answer one. Let's see. Somebody's asking, what is plasma? And Okay, that one is fairly easy. Let me do that one and I'll do one more. Okay, plasma. So normally there are three famous states of matter, phases of matter: solids, liquids, gases. There actually are other phases of matter that people don't talk about quite so much, that, for example, gels. I mean, for example, we are not obviously either solid, liquid, or liquid. We're kind of mushy stuff. And that's kind of more like a gel. And that's a typical thing you get with long, complicated molecules that you don't get with just sort of single atom kinds of materials and things. But okay, plasmas are something different. Plasmas are what you get when you heat up any material. Normally, the atoms have protons in the nucleus. And so an atom, depending on its atomic number, depending on its atomic position in the periodic table, it will have some number of protons. So hydrogen has one proton, helium has two protons, and so on. In the normal state of the atoms, the number of electrons is the same as the number of protons in the atom. So ordinary hydrogen has one electron, one proton. Ordinary helium, two electrons, two protons. But you can do what's called ionize these substances by, if you heat them up, if you pump enough energy into them, you'll pull the electrons away from the nucleus. You'll be able to overcome the electrical forces that hold the electrons close to the nucleus, and you'll be able to tear them away. And then you'll have a so-called ionized atom, which doesn't have its full complement of electrons. And so that ionized atom is what you have in a plasma. That's what you have in fire, for example. It's what you have in the surface of the sun. These are plasmas that have electrically charged things in them, not ordinary neutral atoms. You know, when you have chemical compounds, the atoms also become ions, but the ions cancel themselves out. So the whole molecule can be electrically neutral, but the individual pieces, like in a sodium chloride table, ordinary salt, that's what happens. It's Na plus, Cl minus. That's because it's acting like one of those things has an electron missing, one of those things has an extra electron, and that produces this force of attraction that kind of holds the sodium chloride together. But when you heat things up, you'll get atoms that aren't electrically neutral, that have their electrons removed, and they have all kinds of weird properties. They have all kinds of properties about the way that they stop electromagnetic radiation. They stop radio waves, things like that. Kind of the most famous plasma, in a sense, in the universe is the plasma that used to be throughout the universe. Back when the universe was very young, shortly after the Big Bang, the whole universe was hot enough that it was all a plasma. And actually, it stopped being a plasma 100,000 years after the beginning of the universe. And so back at the very, very early parts of the universe, it was so hot that there weren't just ordinary hydrogen atoms. There were separate electrons and protons running around, and it was essentially a plasma of hydrogen gas. And so that meant that it was, so one of the consequences of that, it was kind of glowing like fire glows, and it was also, you couldn't see through it like you can't see through a piece of fire. So that was, so 100,000 years after the beginning of the universe was all a non-see-through glowing plasma. The question is, what happened to that plasma? Okay, so this is so here's a question. If you look, you know that it takes light a certain time to come from, let's say, a different star or a different galaxy. Like, takes light 8 minutes to get from the sun. It takes light 4 years to get from the nearest other star, Alpha Centauri. It'll take so some other galaxy, it might take 1 million years for light to get to us. So as we look out in the universe, we see light that started its journey towards us a really long time ago. And so one thing you might ask is, if you look out and there's no galaxy in the way, and just look out to the edge of the universe, what do you actually see? Well, what you see is light that came to us from, essentially what you're seeing is that plasma that existed 100,000 years after the beginning of the universe. Because, and it's a little bit, the geometry is a little bit complicated, but essentially the light that you see in any direction comes from the kind of the reduced the kind of cooled down, longer wavelength version of light that started from the plasma that existed 100,000 years after the universe began. So in every direction that we look out in the universe, we see the kind of this thing that's called the cosmic microwave background. It started off as visible light, but because of the expansion of the universe, it's now turned into microwave radio waves. And we see in every direction in the universe, we will see that radio signal. And actually what happened, that was originally discovered in 1964, I think, by a couple of people at Bell Labs, the company that operated the US phone system, the precursor of AT&T. They were using satellites and things like this, early communication satellites, and they wanted to get, they were measuring the radio emissions, and they wanted to get really sort of low noise radio emissions from their satellites. They were measuring, how much, could they, how well could they sort of listen to the radio signals from the satellites? And they were very frustrated because there was a background. There was a radio noise at very low intensity radio noise at this very specific thing that corresponds to a temperature of about 3 degrees above absolute zero. That they were sort of very frustrated. They just couldn't get rid of that radio noise. And eventually it was realized that actually that radio noise is just a feature of the universe. It comes from, it is the sign of it's the sort of signature of the Big Bang, and it's what we detect from that. So that was now I'm forgetting what question I'm even answering here. Gosh, that was terrible. Oh, I was talking about plasmas. Yeah, I was saying that that's the plasma that the plasma from the early universe. The sort of last vestige of that plasma is the cosmic microwave background. Okay, so last question I'm going to answer here. What's the likelihood that there's another universe exactly like ours out there? That's a very interesting question. It's hard for us to know. Let me tell you something that really has surprised me. So let's imagine that we know the exact laws of physics, the exact rules that determine how our universe works. Okay, so we know these exact rules. We can, then we've solved the sort of fundamental theory of physics. We know the rules for the universe. We can say, this is how our universe works. Anything we want to work out about our universe, if we had a big enough computer, and big enough might mean a computer bigger than our universe, which means we're out of luck because the best we can do is use a computer that's in our universe. So we wouldn't actually be able to work out what our universe will do, but at least in principle, we would be able to work out what our universe would do if we had a big enough computer, even though we couldn't actually have the computer that big. But so if we know the rule for the universe, then we can in principle work out everything about our universe. So then the immediate question is, okay, we know the rule for the universe, and actually I'm galloping along, getting close to being able to find that rule. And okay, so we know that, let's say we know the rule, and we hold it in our hands, we put it up on our computer screen, here's the rule. It's some particular mathematical like thing, it's the rule for our universe. So the next question we'd ask is, okay, why did we get this rule? Why were we assigned? Why was our universe assigned this rule? I mean, there might be an infinite number of other possible rules. Why did we get this rule and not another rule? Okay. And I thought that question would be unanswerable. That is, I thought that there would be no scientific answer to that question. But I just had this sneaking suspicion that there might be a scientific answer to that question. Okay, and here's roughly how it works. And it turns out it looks like there is an answer. Here's the thing. If you are an observer, a creature, an organism, a brain, whatever, in a universe, you are observing that universe. But the rules, the laws of physics that are governing how your brain works are the exact same laws as the laws that are governing how the universe that you're observing works. So there's this kind of funny interplay between you as the observer of the universe being governed by certain rules and the universe that you're observing being governed by the same rules. And so I just had this sneaking suspicion that it might be the case that essentially every universe, every possible set of rules to an observer who operates according to the same set of rules will in a sense look the same. So if you were outside the universe and you didn't operate according to the rules of the universe, you would say, oh, this universe works such and such a way. But if you're embedded in that universe, you might say of two different universes, with different rules, you might say, oh, those universes work differently. I can see that from the outside. But if you're embedded inside that universe, operating yourself according to the rules of that universe, you don't get to see that. You can't tell. And actually, it's for physics types, it's similar to the way relativistic invariance works, and the independence of I can talk about relativity some other time. In any case, so the surprise thing that I figured out about a month ago actually is that it really looks like we're it. There's only one. In other words, all these different possible rules that you might use to describe the universe are all, to an observer within that universe, all in a sense look the same. So it turns out there's a bunch of footnotes to this. There's a bunch more complexity to exactly how this works. But in some sense, every universe that works according to rules that are even vaguely like the rules of our universe is equivalent to an observer in that universe to the exact same universe. So to my surprise, I think there's a scientific argument that says there's only one universe. Now, to say there's an exact copy of our universe, yes, we can't tell that. We can't tell the difference between those things. But to say, oh, there are different universes and they operate according to slightly different rules, I think that won't work. Now, there is a footnote to that, and it's for another time, and perhaps after I have a chance to describe my whole big physics theory. But the footnote has to do with what kinds of computations can happen in the universe and whether we can do hypercomputations and other such things. I think that's a topic for another time. I'd be really happy to talk about it. And you guys are asking such fun questions. I'm really, I hope you find it interesting. And I hope while we're all stuck with that nasty 29,000 base pair sequence attacking us and trying to replicate itself, we can at least have some fun talking about science. So I'd be happy to do another one of these. I can talk about science. I could talk about technology and how some technology could try and answer questions about how various kinds of technology work and so on. It would be great to get some feedback from folks who've been here to tell us what things I was talking about that were just boring, incomprehensible, kind of what people were interested in and so on. Now, on my effort to always do something different that I've never done before, I'm actually going to do another session on Thursday, and it's going to be about math. And I'm going to try and talk about fun with math. And that will be aimed at, I think, let's say 10 and up folk. I hope I'll have things to say that will be a little bit surprising even to people who are who know lots about math. But I think I'm going to aim it, I hope, at if you kind of understand arithmetic decently well, you should be able to understand what I'm talking about. And so I will be doing that on Thursday, and I will try to explain some fun things about math. And yeah, so I hope you enjoyed this. I had a good time, and maybe I'll see you all again. I'll probably do another one of these probably next week, and as I say, math on Thursday. Okay, thanks for joining us, and see you another time.